calculus related rates problems. Here we're going to go over some problems similar to the way we did in the first semester, except these ones here have an extra degree or layer of difficulty, including trigonometry in one of these three problems. Problem 1, a small balloon is released at a point 150 feet from the observer who is on level ground. And so I'm going to just make a sketch here while we read the text. So here we have 150 feet. The observer is away on level ground from where a balloon is released. If the balloon goes straight up at a rate of 8 feet per second, okay, so we have this balloon that has gone up at a rate of 8 feet per second. So I'm going to write this up here, and we're going to set this up kind of as an XY coordinate plane. So we'll say X, Y, and so we're going to say dy dt, the change in the Y with respect to time, is equal to 8 feet per second. How fast is the distance from the observer to the balloon increasing? So here's our observer right over here. Our observer is observing this balloon right up here. Okay, so there's our observer, there's the line of sight. And how fast is the distance from the observer to the balloon increasing? So we're going to call this value Z. Okay, this is Z. When the balloon is 50 feet high, and so this balloon is 50 feet high at the critical value we're evaluating. So the format we have for this is called F, W, G, E. Okay, find says how fast is the distance from the observer. So Z is this distance, and so we're looking for the change in distance with respect to time, dz dt. When, okay, we'll say y equals 50 feet. That's going to be our y value. By the way, our x value is 150 feet. Okay, we're given, as I just said, x is equal to 150 feet. Or dy dt is equal to 8 feet per second. And what else? Okay, what is our equation going to be? Well, our equation is going to be a version of the Pythagorean theorem. A squared plus b squared equals c squared, or x squared plus y squared equals z squared. So we'll say z squared equals x squared plus y squared. And we're going to take this equation up here, and we're going to implicitly differentiate both sides of this equation. So the derivative of z squared is going to be 2z dz dt equals the right side of the equation, which is going to be 2x dx dt plus 2y dy dt. Now, we don't have what z is yet. To find z, we're going to use Pythagorean theorem. So z is going to be equal to the square root of 150 squared plus 50 squared. So z It's going to be approximately equal to, go to our calculator, and we're going to clear this out of here. Okay. The square root of 150 squared plus 50 squared. So we're going to get 158.13 feet. 58 point, what I said it was, 58.11 feet. So we have 2 times 158.11 equals 2x. Well, x is 150, but there's no dx dt. There's no movement in the x direction. So this whole thing here is going to be zeroed out. So we're left with 2y, and y is 50 feet. And then times dy dt, which is 8 feet per second. And so now, and we have here, that's going to be dz dt. So 2 times 158.11 dz dt equals 2 times 8 times 50 times 8. So we have 2 divided by 2, cross out these 2's. So dz dt we're going to get by taking this 50 times 8, which is 400, divided by 158.11. So dz dt, let's get our calculator out again. We have 400, and we're going to divide by, we're going to take the answer in pure form here by pressing second, the negative sign for a and s. So we get 2.530, it looks like. So 2.530 feet per second. And before we go on from here, does this answer make sense? Well, we know that the distance has to be increasing, so we have a positive 8 going up here, and this dz is going to have to be positive also, but not as much. So the answer makes a little bit of sense at least. Okay, let's go on to problem 2. Sand is falling off a conveyor belt at a rate of 12 cubic feet per minute into a conical pile. So we have this sand falling, and so it's going to be dv dt, the change in volume with respect to time is going to be 12 cubic feet per minute. So feet 3 per minute. It's falling onto a conical pile. So I draw a pile here, and so here's our cone drawn. Okay, so that's kind of what this looks like. And the diameter of the pile is 4 times the height. At what rate is the height of the pile changing when the pile is 10 feet high? And so we're going to start out with the height of the pile equaling 10 feet. Well, if the diameter is 4 times the height, d is equal to 40, because that's going to be 4 times the height, but the radius is going to be equal half the diameter, or 20 feet. And we want to find, as this pile is having sand added to it, what is the height, or what rate of change is that height of the pile changing? So the height is going to be dh dt. So I'm going to come over here the left and put the letters you know well, F, W, G, E. Okay, we're trying to find dH dt when height is equal to 10 feet, given, well, we know that we're given dV dt is equal to 12, and then also R is equal to 20. So there's a relationship. So R is equal to 2H. That is something we're given. What is our main equation? Well, the equation that we're not given in the text of the problem is the volume for a cone. And it's going to be 1/3 times the area of the circle of the base, which is going to be pi r squared times the height of the cone, which is h. Now we happen to know that the radius is equal to twice the height. And so what we can do to make our life easier is eliminate the variable r by replacing it with 2h. So we can rewrite this equation as v equals 1/3 pi, and in the place of r we put 2h and square it and multiply by h. And then we can come up here. I'm going to rewrite the equation up here. V equals 1/3, and I'll put pi, and then 2 squared is 4 times 4, h to the 3rd power. And now, implicitly differentiating on both sides, we have dV dt is equal to 1/3, and then we multiply by 3 in differentiating. So 3/3, that comes from this h to the 3rd power, times pi times 4 h squared times dH dt. So now we have an equation we can start putting things into. And so dV dt is 12 equals 4 pi, and our height is 10. So here we have 10 squared times dH dt. And then on the right side, 4 times 10 squared, that's 400. So 400 pi dH dt. And dividing by 400 pi, we have dH dt is equal to 12 divided by 400 pi, and 12 over 400 pi simplifies to, we divide the numerator and denominator, each of them, by 4. We're going to get in the numerator 3, in the denominator 100 pi, and this is going to be in feet per minute, right? Because cubic feet per minute, feet per minute. And this is going to be our answer here. Okay, the last problem we're going to do is this hot air balloon problem. So in some ways it looks similar to problem 1. It rises straight up from a level field, is tracked by a rangefinder 500 feet from liftoff point. So here we are with we have 500 feet from a liftoff point. And when we set this up in an XY coordinate plane, we can say x equals 500. And the balloon is going straight up here. And so we're going to draw our little balloon again. Here's our balloon. It's going straight up. And there's the viewer, or the rangefinder, we'll say we have an operator of a rangefinder over here, is looking up at this balloon. And the angle between them, theta, is equal to pi over 4 radians. So now the rate of the angle increasing, the rate of angle we're going to call d theta with respect to time is going to be 2/45 radians per minute. Okay, now we're trying to find the rate the balloon is rising, so that's going to be dH dt. That's what we do not know, and we're trying to find out. So that is our question mark here. Okay, now one more thing. How can we find this y value? Well, what do we know about an angle, the angle of pi over 4? What we know is that's the angle in a 45, 45, 90 right triangle, which means that we know that y, this opposite side here, is also going to have to be equal to 500 feet. Okay, now let's go ahead and write out our, organize our facts here. Find, we're trying to find dH dt, and if the balloon is going up, we know it's going to be a positive number. When I guess y is equal to 500 feet. We're given x is equal to 500 feet. We're given d theta dt is equal to 2/45 radians per minute. And what is our equation going to be? Well, our equation is going to be the tangent of our angle theta is going to be equal to our opposite side, which is y, over our adjacent side, which is 500. Now we know that our opposite side at this time is going to be 500 as well. We're going to need to have a variable on both sides of this equation in order to perform a related rates equation, or to obtain one. And so we're going to go ahead and take this equation up here and differentiate it. And what we're going to have is, what is the derivative of tangent theta? Well, it's going to be secant squared theta d theta dt. And that's going to be equal to, on the right side, of dy dt over 500. So now we can, or I'll just say dH dt, right? So let's do it that way because we're looking at change in h. So let's go ahead and work this out. Okay, one thing we can do is we can rewrite the left side as d theta dt over, what is the reciprocal of secant? Well, it's going to be cosine. So over cosine squared theta is going to be equal to dh dt over 500. So dh dt is going to be equal to 500 cross multiplying 500 d theta dt over cosine squared, I'll say cosine squared pi over 4 because that is our angle. And so that is going to be 500 times 2 45ths, and then also in the denominator we're going to have cosine squared pi over 4. Well, what's the cosine of pi over 4? It's going to be square root of 2 over 2. So let's go ahead and put that in our calculator. We're going to have 500 times 2, or 1,000. Here's our calculator. $500 times 2 is 1,000, divided by 45 times square root of 2 over 2. And we're going to have to square this because we have cosine squared theta. That should be this. So 400 ninths. Let's change that into decimalized versions. I mean, see what we get here. If we go to math, 2, 44.4. So we have 44.4 feet per minute. It's going to be our answer here. I think that's going to be it. I'm going to double check it. I think that'll be good. So anyway, that's it. I hope this has been helpful to you. Good luck, and thanks for viewing.